Morning, everyone. Today's video is on um, Chapter 6, Rapid Thermal Processing. Don't have any administrative announcements today, I don't think, unless I'm forgetting something. So I'll just jump right into the notes. They are posted on Teams. This will be the last lecture for the current homework set, which is due on Monday. Okay, so rapid thermal processing. What are we talking about? Well, the name kind of gives it away, right? We are doing a thermal processing step, right? And we're doing it quickly. Why do we need to do it quickly? Well, as we talked about yesterday, right? We implant impurity atoms, we call dopants, to modify the electrical properties of silicon over very small and very precise regions of silicon. Right, we're going to dope, say one region N-type, where we're going to add a group 5 dopant, and that's going to be immediately next to a region that is P-type, where we're going to add, a group 3 dopant, which is an electron acceptor, right? So we're putting these dopant atoms in very precise and very small regions on the silicon. We want them to stay there. However, they don't care what we want them to do, and if we increase the temperature of the silicon at some later point, those atoms are going to move around via diffusion. And so if we have high concentrations in the regions we want, if we raise the temperature, right, those concentrations will migrate and change the distribution to something that we didn't design. And so we know that diffusion is driven by two things, right? Temperature and time. And the more that you have of either one of those, the less you need of the other, right? Meaning, if you raise the temperature, right, the fusion is going to happen much more rapidly. And in many cases, we take advantage of this by doing a thermal processing step at a higher temperature so that it doesn't take as long. Or if you need to have a temperature for a long time, right, then you need to keep the temperature, or you need to, then the temperature that you keep it at needs to be relatively low. And so diffusion after you implant your dopants is undesirable. And so if you want to prevent a diffusion, right, you need to reduce either the temperature or the time. Reducing the temperature is not always an option, right? For example, you might have to raise the temperature to anneal the ion implantation damage. Remember, we talked about in the last video about how implanting all of these ions, it's done at high velocity, and the ions coming in bounce around many times before they lose all their energy, and this knocks lattice atoms off of their lattice location and disrupts the crystalline structure. If you have a high enough dose of ions, you can make the material fully amorphous. And this isn't good. We spent a lot of time making a perfect single crystal or a high quality single crystal, and so we want those silicon atoms to be on the lattice site. We want the impurity atoms to be on a lattice site, and so we anneal it, right? We raise the temperature high enough that those ions become mobile enough that they can then reestablish that crystalline structure, right? That's the lowest energy arrangement. It's going to naturally, spontaneously get there as long as those atoms are mobile enough. So we need to increase the temperature to heal that implantation damage, but we don't want to have the temperature high enough for long enough that we get diffusion and redistribution away from the dopant distribution that we intentionally created. So we can't reduce temperature, so we're left with reducing time. We can reduce the amount of time spent at high temperatures to reduce the amount of diffusion that occurs. And this requires us to complete our heat treatments rapidly. And doing something quickly is challenging in its own right. One reason is that right, we're making many devices simultaneously on a large silicon wafer. Right, this is one of the ways that we make these devices economic. Right, so if we can make 1,000 at a shot, right, then we can, it's going to cost 1,000th of the price, or but that means that you want to have the same device quality coming out of a location, say near the center of the wafer, the silicon substrate, and from the edge, right? So if you're going to do this rapid thermal processing, right, you need to make sure that your temperatures are uniform across the surface so you get the same result all across your wafer. And so you need to heat and cool the surface uniformly to achieve that. You also need to measure the wafer temperatures so that you can monitor what's going on in your processing and adjust your heating, your environment to maintain a certain thermal profile that you desire. Luckily, this is enough, right? You can anneal damage very rapidly, and so you can heal that damage in the crystal. You can activate the impurities, meaning you can move those to a lattice site so they become part of the crystal, the silicon material, very quickly, right? So short times is enough for annealing damage, right? So you can get the annealing that you want and avoid the diffusion that you don't want. This also, as we'll see later, can be used to grow thin oxide layers, which are beneficial as our devices get smaller and smaller. The oxide layers need to get thinner as well. Okay, so we need to heat the wafer, heat the surface very rapidly. So what methods can we use? Can we use a laser? Well, no, it's not the best. It can heat the surface very quickly, especially a pulse laser, right? It can heat the surface so quickly that you would ablate the very top layer. But lasers can be difficult to control, the temperature and the time, and that that deposition into the upper surface, especially from a pulse laser, produces very large thermal gradients. Not to mention that buying and maintaining a laser is difficult and expensive, especially on an industrial scale. Becoming less so, but still, if what you want to do is heat something, there are better ways. So if a laser won't work, can you use an electron beam? Not really. To heat the surface uniformly, you need to scan the electron beam very quickly. And so you're not heating the whole surface at the same time, which makes getting uniform temperature across the surface difficult. And so this is an example of where a simple solution is the best one, and that is just a lamp, right? So in a lot of applications, we're seeing, incandescent type bulbs kind of fall by the wayside, right? In residential, you're getting to buy them in stores. Really, they've got compact fluorescence now. LEDs becoming cheap enough that that they are the go-to choice. And that's because in residential applications, we don't want the heating. What we want is the light. But for rapid thermal processing, right, what we want is the heating. And so an incandescent lamp is cheap, right? It's just a glowing filament. It's a little bit slower, but that's actually, it's still within the rapid thermal processing regime, right? Slower in the sense of a minute or two, not a second or two like a laser. And so the temperature gradients are much less than you might see with a laser pulse. And so rapid thermal processing uses lamps for surface heating. And so if you're going to use a lamp as a heat source, and considering rapid thermal processing, right, as a thermal problem, it's all about the heat transfer. And so in any heat transfer problem, right, you have a couple of mechanisms for heat to move around. There's conduction, convection, free convection, forced convection, and then radiation. And so the lamp will kind of lend itself to certain of these mechanisms, but just by way of review, when we're talking about conduction, right, we're talking about heat transfer through a solid via contact. This is important in rapid thermal processing, not to get the heat into the wafer, but to consider the heat flow as it moves from the surface where it's deposited into the bulk. But it wouldn't be a very good way to heat the wafer, because that contact would generate a lot of surface imperfections. As we'll see later when we talk about contact photolithography, right, that's the main drawback there, is that anytime you have contact, you have the possibility of creating surface imperfections. So conduction in functional form is shown here. This dot is basically the derivative, so we're seeing the change in Q, or the change in heat as a function of time, is dependent upon the thermal conductivity, the cross-sectional area of contact, and the thermal gradient. Convection is another thermal transfer mechanism, and it can be either free convection or forced flow, the difference being that in free convection, the fluid medium moves due to density variations, right? Hot air rises, and so you're not driving that flow. Forced flow would just be the opposite, where you have a fluid surrounding and transferring heat, but you are driving that flow, say, with a fan or some other means. Convection, I suppose, could work if you had a clean gas flow, with few particles, but convection is generally relatively slow, so not really helpful if what we're doing is to heating it quickly. Convection here, right, we have change in heat with time, is usually modeled this way, where you have, and we saw this in our Deal-Grove model, right, where we have some mass transfer coefficient and some thermal gradient between the surface and the surrounding fluid. Okay, so conduction is good, but not for heat transfer into the wafer. Convection is not so useful. So the last major heat transfer mechanism is radiation. What we're talking about with radiation is heat moved via emitted and absorbed photons. So this is good for microfabrication, processing, and reducing surface imperfections, because you don't actually have any contact between your heater and your surface, or even any contact between some medium and your heater and your surface, right? Absorb photons, carrying, carrying no mass, and so there's no possibility for contamination of any particles. If we choose a lamp as our heat source, then our radiation will be broadband and incoherent. Right? This is different from a laser source, in which case you would have very narrow band and coherent radiation. And so what we're essentially talking about with a lamp is a black body. And a black body is everything radiates. A black body, I guess, is a perfect radiator. So if you had let's say, a chamber that was heated to a certain temperature, and then you put a small hole in that temperature, right? You would have radiation coming out of it, and basically very little going in. And it would describe the maximum amount of radiation that you would get as a function of temperature and wavelength from any body at a certain temperature. And the black body expression is shown here, right? M is used for emittance. So we have emittance as a function of wavelength, and temperature is given by this expression here. And so we have a wavelength dependent and temperature dependent expression modified by a constant that is a function of wavelength. This constant epsilon we call the emissivity, and that modifies the black body by a constant that can change with wavelength. If this is anything, if this is 1, we call it a black body, meaning it's a theoretical maximum. If it's less than 1, but constant, right? If there is no wavelength dependence, we would call it a gray body, right? Because it's something less than black. And if it does have wavelength dependence, which most things do, we would call it a selective emitter. But in general, black bodies describe emittance, and the general trends are that as you increase temperature, you get more radiation overall, and also the peak shifts to lower wavelengths. And the black body, as I said, right, is the theoretical maximum at any given wavelength, and the emissivity modifies that by some constant, something less than the theoretical maximum. And so if you have a lamp that is heated to a high temperature, then it is going to emit a lot of energy via radiation, and that can be used to heat the surface of your wafer relatively quickly. Before I move from this page, if you integrate the black body expression over wavelength, right, you get the Wien's displacement law, which shows the total emission from a black body over all wavelengths, and it increases as t to the fourth times a constant, and then times your emissivity here. And so you can see here this t to the fourth describes the very intense dependence on temperature of the overall energy coming out. Right. This is also going to mean that as our wafer gets hotter, it is going to be emitting also. And so to get hotter and hotter wafer, we're going to need to dump more and more energy into it via these lamps. And I'll do an estimate on the next page or two to kind of justify or just how many of these lamps are required. And so as I said, right, on the previous page, here's just a kind of a picture of it. You get a distribution of a black body as a function of wavelength for different temperatures. And so here we have the emittance, right, in watts per area. And as you go up in temperature, right, so the dotted line is 3,000, the dashed is 4, 5, 6,000, right, you're going up in overall intensity, meaning the integrated area under these curves goes up very rapidly as I increase temperature. And also the peak emittance, right, the highest emittance, the wavelength of highest emittance for each of these black bodies is shifting to lower wavelengths as you increase the temperature. Okay. So if you choose a black body and use a lamp, so what happens, so as we are heating the surface, the emitted photons are reaching the surface, what's happening, right? So, in all optical processes, you have a couple of general processes that can happen, right? That photon can be reflected, can be absorbed, and then re-emitted, or it can transmit right through. For silicon wafers, generally they are opaque, right? So we can kind of neglect the transmissive part for wafers that are thick enough. And so we can estimate the emissivity. So if this is 0, then every photon must be either reflected or absorbed. And so if it's in equilibrium, right, every photon that's absorbed is also re-emitted. Otherwise, the temperature would change. And so we have the emissivity here equal to, right, so it would have the absorption and re-emission plus the reflection would equal 1. If I subtract the reflection from 1, then I can get an estimate for what the emissivity is by measuring the reflectance. Okay, so how do we get the heat from the heating element from the lamp to the wafer, and what is going to modify how much of that energy makes it from one to the other? This expression here from Campbell kind of describes some of these factors, right? So we have S, which is the heat transfer, the net heat transfer, right? So we have the heat flow from, say, 1 to 2. That would be, say, from the lamp to the wafer. And then we're going to subtract the heat that flows in the opposite direction, right, from the wafer back to the lamp, right? Because as the wafer gets hotter, right, it becomes a black body of its own and is re-emitting some of that energy. And so the overall heat transfer from the lamp to the wafer is going to depend on the relative temperatures of the lamp and the wafer, right? And so it's kind of competing black bodies in a sense. And because they're competing black bodies, right, the emissivity is also going to come into play, where I'm looking at essentially the emissivity and the temperature, right, and this constant here from the Wien displacement law that we showed on the previous page, right here, describing the total emittance of energy across all wavelengths. And so I have kind of, like I said, dueling black bodies as far as energy transfer. And then also the areas involved and the view factor. So what I mean by view factor is sort of, how much area is being exposed, right, between the two. And so if you move them further apart, right, just like, the sun only occupies a small part of the sky, as you move further apart, right, that energy that's being emitted in all directions, right, a smaller portion of it is actually reaching to your target. And also, as you move to the side, right, the angle is also going to reduce the area that is being exposed, right? You kind of have this oblique exposure as you go to higher angles. And so you want to increase, right? Obviously, I want to maximize this heat transfer, right? Because I'm trying to heat the wafer, and so I'm going to run my lamp at a higher temperature, as high as I can run it. And I'm also going to do what I can to increase the view factor, right? One way it can do this is by using reflectors to redirect radiation that is sent in some other direction to my intended target. Okay. So, so what sources can we use? Should check the time here. Okay, about halfway. We can use a tungsten halogen lamps where we have a tungsten filament that is resistance heating. So we drive a current over that filament. The resistance of that flow leads to Joule heating. And so I just heat that resistively to a high enough temperature, and it will start to emit like a black body. The halogen gas inside of the glass envelope where the filament is not there to contribute to the light emission, but it's there to keep the tungsten from plating on the quartz envelope of the lamp. So not only is it emitting radiation, but it's also boiling off some of those tungsten atoms, which would normally leave the filament and travel in line of sight and deposit themselves in the quartz, eventually, shading out the filament. And so the halogen gas just reacts with those tungstens and redeposits them back on the filament, so you have a longer lifetime for your filament. You can also heat with a glass discharge where you have a plasma that is your emitting source. In any case, these are relatively low efficiency, and so you need a lot of power here. And before we move from this, I did a little bit of a kind of a back of the envelope calculation here to estimate sort of the order of magnitude you would need to heat a wafer up to the kinds of temperatures that are required for rapid thermal processing. So the first thing you would need to do is to estimate, okay, how much power do you need to heat up a silicon wafer to a certain temperature? And so here I'm kind of assuming that radiation from the silicon wafer is the dominant heat loss mechanism. So it's becoming a black body of its own. This is assuming that there's not a really strong convective flow within the chamber, and also that it's thermally isolated, so you're not going to get a lot of thermal loss. So mostly it's just radiation from the hot silicon wafer itself. So if we're heating it up to 1100 C, right, that's 1373 Kelvin, so we'll plug that in for T. So T to the fourth times the constant for sigma, and we'll assume, if we go down here, we can see that silicon at high temperatures has an emissivity of about 0.7, so we'll plug that in here for 0.7, which gives us a total emittance at these annealing temperatures of 1.4 times 10 to the fifth watts per square meter. We'll do a little bit of, multiply that by 10 to the fourth to convert from watts per square meter to watts per centimeter squared, which is a more useful unit. And then we'll say that we have a wafer that is, say, 15 centimeters on the side. So if we have, 15, a relatively small wafer, so 15 square centimeters, gives us a total emission from that small wafer of about 3 kilowatts. So in order to keep it at this temperature, right, we need to supply that much, at least that much energy to maintain that equilibrium, because that's how fast we're losing it. And so if you look at the light from the lamps, you could say, okay, well, I started with some amount of power, and then I don't convert it completely into usable light. So we'll say 40% conversion efficiency. And then we'll say our reflectors are able to direct 30% of that's produced to our wafer. And so we need to end up with this much. So accounting for those losses, right, if you divide these over here, you get about 25 kilowatts of power acquired. Now if you have a filament, filaments produce about 100 watts per centimeter. And so to get 25 kilowatts, right, you're going to need 250 centimeters worth of filament. That's about 100 inches, right? So you could think of it, if we had an 8-inch lamp, you'd need about 12 of them directed onto your silicon wafer, right? So you need a lot of lamps, a lot of power to heat these up to these kinds of temperatures. Okay, so that presents a challenge, as we've said before. You want to get the temperature uniform across the whole surface, and you can improve the uniformity of the temperature by creating by how you arrange your lamps and any reflecting cavities that you were to put them in. This is made more challenging by the fact that, remember, your wafer is losing heat via radiation. And so the edge has more surface area with which to emit, and it's going to have a higher loss, and so you're just generally going to have cooler regions near the end, which makes it hard to have a really uniform surface. So in order to account for that, you might actually want to have more incoming radiation at the edges of your wafer to increase the uniformity. Overall, you may, if you have many lamps, which we know we're going to need many lamps for a large wafer, you could actually set up a system where you have independent control over many different heating elements, and you monitor the surface uniformity and tune how much current you're sending through each of these filaments and how much radiation they're giving off to create a more uniform surface, right? But you can imagine this is a difficult feedback and temperature control problem. But the motivation is there for these companies to solve this. Here's an example of what I'm talking about with a reflector, right? If I have a lamp here, right, any of the radiation that would normally go off in some other direction is redirected back through this window at the wafer, which can increase the view factor and decrease the amount of energy generated by the lamp that does not go into heating the surface of the wafer. Okay, so if I'm going to have multi-zone heating and feedback control, that does me no good if I don't actually know what the temperature is on the wafer and how uniform it is. So I need to have some means of measuring the surface temperature if I'm going to have closed loop control to maintain a certain temperature and a certain uniformity across the surface of my wafer. Normally we would measure temperature with a thermocouple. This is two different metals in that produce a potential difference at different temperatures. But this is difficult to do with silicon wafer because there's not really anywhere to put it. You would need contact with the surface, which is problematic. Also, the thermocouple makes a measurement by having energy flow into it, right? And so this naturally changes the thermal distribution in the region around the thermocouple, and so the measurement itself changes the temperature of the surrounding material. And like I said, any opportunity for contact here is an opportunity for surface contamination. So thermocouples, contact measurements are not good. So we want some indirect way of measuring the temperature of the surface, and there's a couple different detectors that can be used to do this. Essentially what they're going to be doing is absorbing some of that radiation that's being emitted from the wafer and producing some sort of a change in that detector that is then correlated to the surface temperature. So you can have materials that change their resistivity and use that as a means for a detector, or you can have a photodetector that actually is another silicon device that absorbs the photons, creates electronic pairs, changes the conductivity, and you measure that as a change in the current that flows through the device. In order to use a photodetector as an accurate temperature measurement, right, you need to know it needs to be well characterized. Depending what the semiconductor material that the photodetector is made out of, it's going to be detecting a certain band of emission. And so here, this emission band, right, now the question becomes, okay, what is the emissivity of our silicon, right, at that emission band, right? Because remember, if I'm looking, let's say here, let's say I'm looking at a, I don't know, 5,000 Kelvin black body, well, if I have a photodetector that's looking in the red, right, versus one that's in the green, right, that could be a factor of 25% difference or something, right? So that's going to throw off my measurement right there. So I need to know what band I'm looking at, and then I need to know the emissivity of silicon over that band. You can say, okay, so measure it. Well, that's difficult here. If you look at this figure here, this shows the emissivity of silicon as a function of wavelength and temperature, right? So we see here that this line wiggles quite a bit, varying from almost nothing to peaking at, like, say, 0.7 as a function of temperature, right? Luckily, as you go up in temperature, right, the emissivity becomes less variable, right? So that's helpful since we're going to be processing these at temperatures that are above 600 C, right? You can see the radiation kind of levels out a little bit, which is good. You also, if you're looking at the surface, right, you want to remove the scattered lamp at the wavelength, right? So you'll have maybe a filter or a window there to remove some of the scattered light from the lamp, as opposed to the emission from the black body. You certainly want to have your detector in view of the heating element. Any optical elements, say windows or lenses, are going to change the amount of radiation that makes it to your detector, so you're going to want to understand the impact of those. Any gases in the chamber also could attenuate that emitted radiation and change how much makes it to the detector. Sometimes you could, and this is common for pyrometers, photodetectors, they actually can look at multiple wavelengths and use that to ascertain the emissivity, right? On the basis that you have a black body, and if I measure it, say, at this wavelength and at this wavelength, then I can fit a black body to those multiple points and extract the emissivity from the measurements itself and not have to know much about the material otherwise. But that's not as helpful as you might hope, because that assumes that you have a constant ratio between those multiple wavelengths, which might not be true either. And this is an optical method. Sorry, my son's coming to ask a question. This is an optical method, and so as we are, say, growing a film, where we'll talk about with growing thin oxide layers, there's the opportunity for interference, optical interference off the surface, and it can help. Maybe you can calculate the emissivity from reflectance measurements, like I mentioned above here, right? If you assume that the surface is opaque, right, then I can make a reflectivity measurement and actually calculate the emissivity in situ. So all of these are things you can do, things that you need to be aware of to make this pyrometer, this indirect measurement, more accurate. But you might say, okay, well, I need an indirect measurement, but this is a lot of complications for a pyrometer, photodetector. Is there anything else? You could monitor the temperature of silicon via thermal expansion. So the rates of thermal expansion and coefficient of thermal expansion are known, and they're less variable than the emissivity for silicon. The problem there is that you would need some sort of a reference mark on the surface that you could track as it moves during the thermal expansion. You might also be able to measure the temperature via the speed of sound, right? Because there's a temperature dependence of the speed of sound in silicon. But I suppose you would need, some contact in order to transmit and receive a signal into the silicon wafer. This is related to measuring the emissivity in situ, but you might actually just be able to look at the reflectance as a function of temperature and extract the temperature that way. And however you choose to do it, right, it's important that you measure the temperature and do what you can to increase the uniformity of the temperature, because if you don't do this well and you have a large thermal gradient across the surface of your sample, that can cause high degrees of thermoplastic stress in the radial direction, right, from the center out to the edges. And this thermoplastic stress can actually produce slip and yielding at the edges due to these thermal stresses, which can warp your perfectly flat silicon wafer, which is a bad day. Okay, so again, what do you get for all of this trouble, right? In building a chamber to heat with a lamp, and measuring the temperature and feedback loops and all this kind of stuff, right? This is a bit of a review here. We talked about this already. The big payoff is that you can anneal the implantation damage from ion implantation without major redistributions of dopants, right? So I am allowing the annealing to heal, or the damage to heal, but I'm not giving very much time for the diffusion to occur and for those atoms to move around. And because they have a strong tendency to do that, because remember, one of the reasons for doing ion implantation is because it allows us to jam more impurities than we would normally be able to diffuse in, right? We would be limited by the solubility limit, but we can basically shoot them in with an ion gun. But if we provide enough time and temperature, then since it's above the solubility limit, right, those atoms are going to come out, and they're going to cluster and they're going to form regions, basically a precipitate of that impurity atom. But we can prevent this by heating very rapidly, which is plenty time for annealing, which happens very rapidly, right, in the order of microseconds, which heals the damage that we want and moves the dopants to the lattice site, but doesn't redistribute the dopants very much. And now that we have this setup, you can actually use it to grow thin oxide layers too. Thin layers are going to grow very quickly, and so if you want a thin layer, you need to be able to heat and cool rapidly. Remember, if we think back to the Deal-Grove model, where these initial growth stages are all in the linear regime, right? So if we look at all of these curves, right, they haven't yet rolled over and reached their limit, where we have kind of a parabolic regime, where these are all initial thin layers that are growing. However, remember one of the difficulties with the Deal-Grove model is that it didn't measure oxide layers. It didn't model them very well when they were really thin. So the Deal-Grove model actually wouldn't be very much help here. This would probably be a trial and error kind of thing. The other thing with rapid thermal processing is that you are reducing the contamination because you're only heating the surface. And a lot of the undesirable reactions are thermally dependent. And so if you only have a hot surface, then you're not, say, blowing off atoms from the sidewalls of the furnace, which could then become incorporated as a contaminant, right? You're limiting the number of reactions that can occur inside of your chamber to the ones that you want to happen. And you can also run rapid thermal processing in conjunction with chemical vapor deposition to deposit other kinds of films. Right, we'll talk about this in a later lecture video. Right, as we add more of these tools to the microfabrication toolbox, you can see how there's overlap, and one could be useful for another, with kind of a hybrid of them. But that about wraps up this video. Remember, we're talking here, this is rapid thermal processing. Again, allows us to heal implantation damage without redistributing the dopant atoms. Thanks.